Welcome everyone to the second lesson of Precalculus, lesson 1.2, which is called Rates of Change. Let's get into it, shall we? A rate of change is where a dependent variable is changing in relationship to an independent variable. Average rate of change is when we look at what happens on average between those changes from a start and an end point. So for us, average rate of change, again, is going to be the change in some sort of dependent variable over some sort of independent variable, or the change in f of x compared to the change in x. So the change in f of x divided by the change in x. We use a little delta, which is a little triangle. It's a Greek letter to represent change. So you might see delta f of x over delta x, or delta y over delta x. Something you might be more familiar with is y2 minus y1 over x2 minus x1. Use it a lot for slope in Algebra 1. Pre-calculus, we use more function notation, so you're going to see more of the f of x2 minus f of x1 over x2 minus x1. But it's the same thing you've been using, the rise over run, if you will. So let's look at a numerical example in the form of some points. And I actually have a numerical representation. I have an analytical representation and a graphical representation all in one for you, so we can kind of see how all of this meshes together. So we have 2 points here. We have 1, 2 and 3, 4. So in this case, 1, 2, we have an x and an f of x and f of x to use in our formula here. It doesn't matter which one you call 2 and 1, because it doesn't matter how the simplification will work. You'll get the same number regardless. If there's negative, you might get a negative on top instead of on the bottom, or you might get a negative on the top and bottom, which would cancel out to a positive, or just a positive, so on and so forth. So we have these 2 points. I like to, as a rule of thumb, use the point that occurs later that has a larger x value first, so that way my denominator is always positive, but you can always do what you want to do. It should work out, as long as you're consistent. So if I am doing the 4 and the 3 together, then I need to put the 2 and the 1 together. 4 minus 2 is 2. 3 minus 1 is also 2. So we get 2 over 2, which reduces to 1. So that would be the average rate of change between the points 1, 2 and 3, 4. What does that look like graphically? Like, how do we represent that graphically? Well, if I draw those 2 points, if I put a point at 1, 2, and 3, 4, and then I draw that line, the slope of that line is our average rate of change. And because these 2 points occur on our curve, this line has a special name. It is called a secant line. So a secant line is a line that occurs from 2 points on a curve. The average rate of change between those 2 points is the slope of that line. In this case, the slope of the line is 1. The line itself would actually be y equals 1x plus 1, because it has a y-intercept of 1 as well. How does that change when we look at tables? So what if I give us a little bit more information than just, here are 2 points, find the average rate of change? So what is the average rate of change on the interval from 13 to 25 seconds? So in this case, we have 1, more information, and 2, we have units, which are going to be very important later on. So we're given a table. T is time in seconds, d of t is distance in meters, which means that t is our independent and d is our dependent. So d goes on the top in the numerator, and t is going to go on the bottom in the denominator. We're going to look at 13 and 25, so we don't care about any of the information except for these 2 pairs of numbers. Remember that the d of t is our dependent, so it's going in the numerator. So I'm going to do 30 minus 76 all over 25 minus 13. So this, when simplified, will become 46, negative 46 over 12, which can reduce because they both are divisible by 2. So that would be negative 23 sixths. 23 is prime, so it can't reduce any further. You can make that into a decimal if you'd like to, but if you don't have a calculator, you can always leave it as a fraction. The important thing we have to add now is the units. How units work for rates of change is it's the dependent unit divided by the independent unit. So in this case, it's going to be meters divided by seconds. So we would put in a fraction meters over seconds. How we would say that verbally is we would say meters per second. So that division turns into a per when we say it out loud. All right. So here comes a big idea. So what if we wanted to find the rate of change at a singular point? This is a calculus concept, but it's important to bring it up now so it doesn't, again, feel like it came out of nowhere later on. So to estimate the rate of change at a singular point, what we're going to do is we're going to use that point and then a point very, very close, about 1,000th off. So if we want to, as it says in question 3, estimate the rate of change at x equals 1 for the function f of x equals negative 1/2 x squared plus 3x minus 1/2, what we're going to do is, well, we need to figure out what the y value is for the x of 1. So we're going to do f of 1, and we'd plug that in. And when you do, you'll end up seeing that that would be a 2. Then we need to pick a value that is really, really, really close to 1. So what I'm going to do is I'm going to pick f of 0.999. That is awful. I would never do that by hand. So what you can always do is you can use your calculator. Plug it into, like, right at the equation as you see, plug it into your calculator, and you can get a very nice estimate that way. Something else that I really like to do is I actually like to put the equation into the y equals screen. So putting it into the y equals screen, I can then bring up a table, and I would love to show you how to do that. Please ask me in class, and I will definitely show you how to do that. But otherwise, we can get that this is about 1.9979995. So the average rate of change for this would be 2 minus this 1.9979995 over 2 minus, oh, not 2, no, 1 minus 0.999. Awful. If we plug that into a calculator, what we're going to get is we're going to get 2.0005. For our class, in Precalculus and in Calculus, what we're going to do is we only leave our answers in 3 decimal places. So for us, we're going to round that up, so that would be 2.001 would be our average rate of change here. You only want to round for your answer. You notice that I did not round for f of 0.999. I only rounded our final answer. So when you do round, only do it at the end, because if you round at the beginning, you're using a rounded answer to get more information, which then makes your later information more inaccurate. So let's try the same thing again here with the average rate of change at x equals negative 2 for the function f of x equals e to the x. So this one is a little bit nicer because we're going to use exact answers, and we'll just plug in the exact answers into the calculator, and that'll give us the approximate response that we'll need later on. So we're going to do f of negative 2, and that would just be e to the negative 2 power. Our calculators can do that. You can do that on Desmos, you can do that on TI-84 that we will have in class. We can leave it like this for now because it's going to make our life a little bit easier. Then we can do f of something really close, 1/1000th off. So I'm going to do negative 1.999. You could do f of negative 2.001. Perfectly fine. That'll again give us e to the negative 1.999 power. And since we're getting approximations, then it really doesn't matter if we go a little above or a little below. We should get something roughly the same. So when we set it up, and what I would set up in the calculator is I would do e to the negative 2, subtract e to the negative 1.999 over negative 2 minus negative 1.999, and that is approximately 0.135. All right, so hopefully not too bad. We're just finding slopes akin to what we did in Algebra 1, right? So positive and negative rates of change. This is a big idea for us because it gives us context into what we're doing and why we're doing it. So positive rate of change, a positive slope, is where when something increases, the other quantity does the same. If something decreases, the other quantity does the same. So you can think of it as increasing over increasing, which gives you a positive over positive, which makes a positive rate of change, or decreasing over decreasing, negative over negative, which would become a positive. Negative rate of change is the opposite. So it would be a negative divided by a positive, a decreasing divided by an increasing, or an increasing divided by an increasing. Increasing divided by decreasing, my bad. Is that a little bit better? No. There we are. We're back. So let's reiterate, shall we? A positive rate of change is as one quantity increases or decreases, the other quantity does the exact same thing. So increasing over increasing, which you can think of as a positive over a positive, which reduces to a positive, or decreasing over decreasing, which is the same thing as a negative over a negative, which would reduce to a positive. Or a negative rate of change is something decreases, the other increases, or vice versa. So you would have a decreasing divided by an increasing, a negative divided by a positive, which would be a negative, or increasing divided by decreasing, a positive divided by a negative, or a negative rate of change. So I like to think of it in terms of the fractions because that helps it make sense in my own brain. So let's determine whether each situation below is a positive or a negative rate of change. So as years increase, our high school's number of students increase. So our high school's number of students would be the dependent, and that is increasing. The years would be our independent, that is increasing. So you have a positive over a positive, that would be a positive rate of change. Then you have, as my weight decreases, the distance I can run increases. So the dependent variable is the distance I can run, which is increasing. And the dependent variable is my weight, which is decreasing. So it would be increasing over decreasing, which is akin to a positive divided by a negative. So that would be a negative rate of change. And that is it for this lesson. If you have any questions or concerns, please make sure you ask them in class. Otherwise, I hope to see you in the next video.